In the first prototype, we showed how connecting inputs and outputs to randomly to a Hebbian neural network automatically gave a novelty maximizing instinct without any objective function or reward function or error function or whatever. But I think people were still unable to imagine how that instinct of maximizing novelty in combination with things like associative learning or just generally just Hebbian, the local Hebbian mechanism can give rise to interesting behavior. So this is prototype number two. It's a simple maze. We have actually just made this as the end of uh, maze, not the whole L. Just to sort of simplify things and make it faster. But even if you make it a really complex maze, it's going to work out. So I'm just going to show the results of what happens if you just randomly connect inputs and outputs to a Hebbian neural network, and you don't even have to give any objective function here as well. So you're not even forcing the system to complete the maze, but it is still sort of learning and improving, and we're going to demonstrate that now. So this code, you can have a look at it from the link that's mentioned in the description. But what happens is, so this is basically the neural network structure. So it's got like 9 inputs, and then like each of it is connected to some 10 or so hidden neurons, and then you have the outputs here. So look at the results here. This is just to see what weight updation is going on and all, in case if you want to investigate. um, so what happens is, initially uh, the network was taking right first, which happens to be the wrong move, and then down. This is so because we made the initial connection weights that way, and we also had a little bit more connections to right rather than down. So 3 rights and 2 downs we had. So initially it was taking right, which was the incorrect step, and then down. And then for the first 2 laps, it was taking the incorrect step first and then the down. But afterwards, it has learned that the right is not learned, as in it has not taken the right step at all. It has just taken the down step within like a few time steps, and it keeps on continuing that forever. So the reason why this happens is actually made in another video. You can actually go and check that out from the channel itself. uh, but this is just to show that you don't need any objective function at all. Just a Hebbian neural network will do a lot of interesting things. And the next prototype that you are going to do is called, the dog and the bell, the Pavlovian experiment. We are going to show that association with the Hebbian network. And again, we are not going to give it any sort of a objective or a reward or error function. It's going to do it on its own. So this is the key takeaway, right? You don't need to give any objective function at all for a Hebbian network. You just make it large enough, and then the thing that we have here is pretty simple. It's just Hebbian rule. We did not even bring in the spike timing dependent plasticity, or we did not bring in 3000 different kinds of neurons, or varying threshold levels, or varying learning rates, or varying decay rates, or anything like that. But so many inputs can be brought in from neuroscience, and then it will make it a much more sophisticated system as well. We just don't have to give it any objective function, because like I said, it already has the instincts to maximize novelty. And in trying to maximize novelty, it will try to move, it will try to communicate, it will learn, do everything. So this is a simple illustration of that. So you're welcome to check this out. And it also helps if people are not in denial of this, and you can't just wait for a single person to just, from their home, uh, you know, build a AGI that's like human level, or it's gonna beat a human in a chess. You can't even make a monkey do that with like, billions of neurons in its head. So this approach needs obviously a lot more funding to, have impressive prototypes, but the word has to spread somehow. So that's what it is.